Okay, I guess we'll start now. Okay, so I'm Nanda. I'm a coordinator in the cybersecurity club at C5, and in this session, we are gonna take a look at writes or execute as a mitigation strategy to overwriting the return pointer. I think you have seen exploits involving overwriting the return pointer in the previous session. And then we're also going to cover how to overcome writes or execute using return to libc. Okay, so I'll share my screen. Okay, is my screen visible?
Yes.
Okay, fine. Uh, okay, so we are going to take a look at writes or execute. So I guess in the previous session you would have seen canary and how to bypass canary and like override the return pointer to spawn a shell, I think. So now one of the ways to like obviously this is extremely good if you are the exploit author, but if you are writing a program, you would want to prevent the misuse of this overwriting the return pointer. So how would you do that? One way to do that is by using this strategy known as writes or execute. So what exactly is writes or execute? It says that a particular page in memory. So how memory works is it's organized into a bunch of pages, and each page is usually around 4 kilobytes. So your operating system will say you want to read a particular block of memory, it'll request a particular page and it'll read that page. So what writes or execute does is it says in a particular page of memory, which is just a particular block, can either be written to or that particular block can be executed as instructions. So why is this helpful? It is helpful because if a particular block of memory can be written to like by the user and can be executed, this is exactly what overwriting the return pointer does. You write to a particular memory address and you execute it. So what this does, it prevents that. It says a particular block of memory can only be written to or it can only be executed. That's why it has an XOR. So what are some pages of memory that can be executed? Obviously, that is your code section in your program that has the assembly instructions. What is the page of memory that can be written to? That is like the stack. So you can write stuff to the stack, but I don't want to execute stuff on the stack because that's what happens when we override the return pointer, right? We like put our own shell code at the return pointer so that when our program reaches that, instead of returning out of the function, it starts executing that code. So this is a strategy that we can use as program authors to prevent other people from exploiting our code. So what this essentially does is it sets a bit known as the NX bit on normal x86 machine, whatever you're running right now on your computer. If you're running a Mac, I think, I don't know what it will be. But on x86 machines, it sets a bit known as the NX bit that tells whether a particular page of memory is either to be written to or it is to be executed. So obviously, this seems like a nice strategy. And like you might feel that whatever you learned so far is completely stopped by this. However, that is not the case. So now, okay, wait. Okay, so you might think writes or execute is an extremely good strategy, but can you think of any example of a program which cannot use writes or execute? Like a program that fundamentally cannot use writes or execute. Uh, You can type your answer in the chat. Like, did you, I guess, okay, I'll explain my question better. Um, Let us say you're writing a program that does something, but you know that for that particular program, you cannot enable writes or execute because by enabling writes or execute, your program is useless. Okay, fine. So an example of a program is JIT compiler. So what is a JIT compiler? You might know if you have used JavaScript, that the you might have if you have used JavaScript, or if you have used let us say PyPy, they are what is known as a JIT compiler. And what does a JIT compiler mean? That JIT stands for just in time. So what it essentially does is it looks at your bytecode and constructs assembly from that, like as the program is running. So this requires it to write to a particular place and immediately execute it as well. So for programs like this, we cannot enable the writes or execute bit, because if we do that, then whatever this JIT compiler writes to the stack, it cannot execute. So that fundamentally breaks the program. So even though writes or execute is a nice method, it cannot be used for every single program. Okay, so now let us come to the point of our attention. We don't care how to protect the program, we want to break it. So how do we break writes or execute? We can, one of the strategies to break this is known as return to libc. So how, okay, so let us look at how we usually did it. In the previous sessions, you might have seen overwriting the return pointer. Essentially, we would fill some bytes with nonsense data as padding. Then we would come to either we try to overwrite RIP or ESP, one of them, either 64 or 32-bit, RIP or EIP. So we will write a bunch of padding data, and then we will write some. We will write the instruction that we want to be executed at the return pointer. This is what is known as read to win type attacks. But if have writes or execute enabled, this obviously prevents us from using these types of attacks, because whatever code we write into the, whatever shell assembly instructions we write into the return pointer will not be executed, because that particular page in memory is marked as only write. It is not marked as execute. Okay, also I forgot to mention why it is known as write XOR execute. You might have seen XOR as a binary operation. It'll only allow, it is set to one if only one of them is true. So it can only either be write or only either be execute. Cannot be both at the same time. That's why it's known as write XOR execute. Anyways, coming back. So as you can see, the normal type of attack that we did before, modifying the return pointer to and inserting our own shellcode, will not work. So how do we prevent this? Uh, okay, so what we do is, it's similar to a normal Stack Overflow attack. The only difference is that instead of overwriting the return address with our own shellcode, we will overwrite it to a pointer in libc. So what is libc? Libc is the standard C library. So if you have used written any C code, um, this stdio.h, stdlib.h, all of these are part of the C standard library. And obviously, all of these functions have to be marked as execute, because they are actually, they have some logic that needs to be executed. So what we essentially do is, instead of writing our own vulnerable, instead of writing our own exploit, okay, wait, let me zoom into the thing. I guess it was not visible. Okay, so I'll explain once again. So what is libc? Libc is a C standard library. So what is a C standard library? If you have written C, the standard library includes functions that are necessary, that interact with the operating system in order to enable fundamental functions such as reading, writing, calling system functions, etc. So this stdio.h is a header in the standard library or libc. You might have also seen stdlib.h or string.h and so on and so forth. All of these are headers in the C standard library, and obviously the functions in this C standard library have to be marked as execute because they are actually executing the code. Puts is a function of C standard library. It has to be marked as execute, cannot be marked as write, because otherwise then the instructions will not be executed, which is not what we want. Anyways, coming back. So libc contains standard functions used by all the programs. Um, and how does return to libc work? Essentially, uh, what we are going to look at is how to invoke a shell, because I think that's what you might have done in the previous session as well. So previously, how you would invoke a shell is you would insert some assembly instructions written as bytes into the return pointer, and they'll get executed. And you'll spawn a shell. However, this cannot be done now. So what we do is the C standard library has a system function that essentially executes anything that's passed into it. And what do we want to execute? Obviously, we want to execute a shell so that we can spawn a shell and run whatever we want. So how do we spawn a shell using the system call? We pass it the path of the executable. In most Linux systems, this would be bin/sh. This is where the shell executable will be stored. So somehow we would have to invoke this system function and pass the bin/sh as a parameter to it. So how would we do that? Um, okay. Let me wait. Before we do this, one thing we have to understand in this particular demonstration, I will show the exploit with ASLR disable. So what is ASLR? ASLR is address space layout randomization, and it is a mechanism to prevent these kinds of attacks. However, there is a way to work around that as well, which we'll explore in the next session. For this particular For this particular session, we'll only look at it with ASLR disabled so that it's easier to understand. Okay. So now, let us look at the extremely simple vulnerable code. We have a vulnerable function which declares a buffer of length 64. However, we allow it to read in 640 bytes. So this might be a programmer error. Someone forgot to use the same constant. They are an extra zero. Obviously, this begs for the buffer to be overflowed and for it to be exploited. So how would we do this? Uh, so now we need to understand how the system function works. As I told before, it needs a parameter that's passed in that it directly just executes. So first, we need to figure out um, how do we get bin/sh to be passed in as a parameter, and then we need to figure out how to call system. So how do we find out where is bin/sh in our code? Obviously, it is not there over here, but bin/sh is an extremely common string. We can find that in libc itself. So let me, okay. I guess you have seen this, right? This is the code that we are going to exploit to spawn a shell. Let me compile this. Okay, I'm compiling it with no py and no stack protector so that I don't want to deal with the canary right now. We can explore a more complex example later. I'm passing in M32 because the 64-bit version is having some issues right now. This was the one that was working anyways. So I compile it, and as we see, GCC helpfully points out that we are reading in more than the buffer, and this could lead to an overflow. Now, what this actually does is when we compile a C program, um, it links with the libc. So libc is the C standard library libc is extremely large, and we don't want that to be loaded into memory for every single C program that we compile. So what essentially happens is libc is running at a particular place in memory, and it's known as a shared library. Every single other C program that wants to call some function in libc will be returned a pointer to the shared library, and from there it will call the function, so that we don't have multiple copies of libc in memory, which will waste a lot of memory. So what the GCC does is it links with libc, and now we want to find out where this libc is. So for that we can do LDD, uh, and this gives us the place that it linked with. So over here we can see that the path is lib/libc.so.6. This might be different for you. You might have a version name also attached. For me, it's not there. But anyways, now okay. First point that we want to do is uh, figure out where bin shell is in our code. It is not there in our code. So the next point that we can find it is in this file. How do we do that? We do that by this. So what this does is it runs the I have a slide for this. So it runs the okay, ignore this. You might have a different, just figure out the path that you get when you run LDD whatever and use that instead over here. Anyways, we use the strings utility, and we pass in certain options. We pass in -a so that it scans the whole file, and then we pass it t so that it prints the offset, which is what we want. We want the memory location. So we want the location of the string in libc, so we want the offset. And then we want it to be in hex. It could be in integer, but then we can convert it back. But anyways, this is just a utility. So this will read all the strings in this particular shared library. And what is the string that we want? We obviously want bin/sh, and that's exactly what we do. We grep for bin/sh, and we figure out that it is at this particular location. So we have to note this down. So it is at 1989C1 for me. It might be at a different offset for you. So we have to keep this in mind. After that, now we have the location of bin/sh. We could have gotten it from another place as well. If instead we had this, then we could directly figure out the location of memory address of S and use that instead. But since bin/sh is not there explicitly in our code, we have to find it from libc. Anyways, now that you have figured out the location of the shell string, we can go back. We have solved part of the problem. Now we have to figure out where system is stored. So how do we do that? Um, as you know, this is an else file. So we can use read else and grep for system. This will give us everywhere that system is used. So in our case, let us use this address 53390. I think, yeah, both of these are same. These other ones are different, as you can see. They're not the system that we want anyways. So now we have the address of system, and we have the address of bin/sh. However, notice that this is not actually the address. This is the address relative to this address. So what GCC does uh, when it links a library with libc is that it sets libc at some particular offset. So that is the offset of libc. This memory location is with respect to this. So the actual address of bin/sh when we are running the program will be this address 0xF7 whatever plus 1989, and the actual memory location of system will be 0xF7 something plus this. Okay, I hope that is clear. So now we have the pointer of system, and we have pointer to the string bin/sh, and we are basically done. We can now give the pointer to system as when we overwrite the return pointer, and this will go into system and start executing that. This will not cause a problem as writes or execute because system is already marked as executable because it is in libc. So as you can see, we have cleverly worked around the fact that even though we cannot execute on the stack, we have cleverly moved around and executed something that is not on the stack but that's on libc, that is anyways already marked as executable. So now it's the usual thing. We just have to find out the padding that we have to give. So I will run it in GDB. Okay, now let me create a simple pattern. Whatever. I'll save that. Okay, I'll run it. I'll copy paste the pattern that was generated. Obviously, it has segfaulted because the buffer was only for 64 bytes, but we have written over 200 characters. Now we can search, we can find the offset of EBP, which is at 72. So what we want to overwrite is um, EIP, which will be 4 bytes from EBP. So that will be 76, 72 plus 4, 76 that we will want to overwrite. So now that we have all of this information, we can take a look at our exploit. Okay, I hope Pawn tools as a library was introduced to you in previous sessions. That's what we are going to be using now as well. So that's what the first line does. It just imports everything. Then we spawn a process with our vulnerable C code. I call the output as uh, vulnerable, like vul. So that's the same name I'm using here as well. That is the name of the executable. Then this is the address of the offset of libc that we got from the linker. So if we look at this, we notice that libc is at this offset. So that is the offset that I've written over here. Then this is the address of system that we grabbed from the reader. So this is the address of system 53390. That's over here. And this is the address of bin shell. And that's it. So we give it a padding of 76 bytes so that we are at EIP. We write our system, then some more padding, and then we write the address to bin shell, and then we send the payload and we'll get a shell. So if I run this, so we have a shell now. So that's how return to libc works. You can check that the NX, that is the writes or execute bit, is enabled. However, we have still managed to bypass it by calling out a function in libc. Okay, so that's basically it. The example I showed was for 32-bit architecture. This it is essentially the same in the 64-bit as well, except that the calling convention for system is different. So we'll have to pop from the stack and then push into a different register so that it works. Right now it is not working for me, so that's why I'm not demoing it. But you can Google how to do that in 64-bit as well. Uh, that's uh, basically it for return to libc. Okay, so this is I guess, a graphical example. So in the previous exploits you might have seen, we would overflow the buffer right to a return pointer, whatever shell code we want, and the return address will point to it and it'll start executing it. However, this won't work when the writes are execute, then the NX bit is set because obviously this part is only marked as a write. It is not marked as execute. So nothing will get executed, we'll just get a segfault. So how do we prevent this? How do we overcome this? Instead of directly executing on the stack, we instead point to an address in libc which is marked as execute. So then we can start. So then it will start executing the function in libc. Uh, that's it really. Okay. If you guys have any doubts, you can raise your hand. Okay. I guess I went a bit too fast. I can go through it once again. Uh, okay, I can go through it from the start. So I guess, okay, wait, I can show you something. So I think in the previous example, you might have had to use -z exec stack for it to work. So what this essentially does is it turns off the NX, setting the NX bit. So if I compile it with this and do that, then NX bit is not set. So this is why in the previous example you were able to overflow the buffer, and if a canary is found, you were able to find out the canary from a format string vulnerability, then put it in the correct place, and then override the return pointer and execute your code. However, most obviously in the real world, programs will not be compiled with this. In fact, programs will not be compiled, will probably have a canary bit set as well. You can try figuring out um, how to exploit it with the canary bit set. It's just combining the two things that you learned from the previous session and from this session. So as you can see over here, if we do not enable the executable stack, then the next bit is set. So the stack is only writable, it won't be executable. I can go through it once more. So what is writes or execute? It's a mitigation strategy to prevent these sorts of buffer overflow attacks that override the return pointer with malicious code. What it does is it essentially makes it assigns pages in memory to either be write or be executable exclusively. They cannot be both at the same time. And this is supported by most platforms. However, there are certain programs that cannot use this, namely JIT compilers. How do we bypass this? We can use return to libc. So how does return to libc work? In the traditional exploit, we just had some padding that we would fill up with nonsense data. Then we'd override the return pointer with a code, usually shell code, that will spawn a shell. However, if the NX or ND is what is set in AMD. I have an Intel machine, that's why it's NX. Anyways, if the ND bit is set, then this will not work. Or um, because whatever code we have overflowed that we have written into the stack starting from the return pointer will not be executed because that stack is only marked as writable. How do we um, overcome this? We simply overwrite it with the return pointer into libc. So since the functions in libc are marked as executable, the program will happily execute that. And libc conveniently has a function called system that takes in a parameter and just runs it. It can be any shell command. In this case, we would actually give it a shell to run. So the path to the command, which would be bin slash sh or bin slash bash, whatever. and it'll happily run that and we'll spawn a shell. How would we do this? We'd first need to find out the pointer of system, and then we'd also need to find out the pointer to a string bin/sh. How do we do that? We'll first compile this. I'm compiling it in 32-bit because it's easier to explain. Once we do that, we find out which libc it is using LDD. So we find out the path of the libc that it linked to. We also given the offset. Once we know the path, we can directly grep for system at that path. We'll get the location of the system function. Then we can find out the location of the string bin/sh using the string utility. Once we have these two, our job is done. We can use the extremely helpful pawn tools library to do this. We have the offset to the libc. Yeah, then using that offset, we have the actual location of system, actual location of the string, and then we simply construct a payload with the padding. Okay, I can show you how to figure out the padding once more. I think this would have been covered previously. Just create a pattern string, then you run the program, paste it. Obviously, this will seg fault because we have pasted a 128 byte string, whereas the buffer is only 64 bytes. Then we simply uh, find the offset of RBP. Okay. Oh, sorry, EBP. RBP is what you would use in 64-bit. Yes, EBP is the pointer just before EIP, so that is 72. So that means EIP is at 72 plus 4, 76. So that's why we fill up to 76. Then we overwrite EIP, which is the instruction pointer, with the address to system. And then we had some more padding. This is the calling convention in 32-bit. And then we pass in the pointer to bin/sh, and that's it. So we send the line, we send it to this process, and then we spawn an interactive shell. Right. If suppose this program was an SUID binary with root, then I would spawn a shell as root, and I would have root access to the system. Uh, does anyone have any doubt? You can raise your hand, and I will let you unmute. Okay, since no one has any doubts, I will end the meeting. Okay, thank you all for attending.